Section 8.2, transformations of logarithmic functions. So now that we've worked with logarithms a little bit and its relation to exponential functions, we're now going to take our base logarithmic function, which is y equals log c of x, and we're going to talk about the transformations occurred on it. So a transformed logarithmic function looks like the following. Y equals a log c base c of b times x minus h plus k. So our a, b, h, and k values work the exact same as any other transformation of any function. A represents our vertical stretch by a factor of a. If a is negative, there's a reflection in the x-axis. B is our horizontal stretch by a factor of 1 over b. If b is negative, there's a reflection in the y-axis. H is our horizontal translation, left to right. H is going to change the vertical asymptote of the domain. So if I move this graph left or right, this vertical asymptote is going to change. So our H value changes the vertical asymptote and the domain. Similarly, how the K value changed the horizontal asymptote and the range of our exponential function. None of the parameters will change the range. So no matter what, the range will always be all real numbers. So given the following function below, y equals log of 1/3 of x, which is an logarithmic decay function, sketch the graph of -2 log of 1/3 x plus 1 minus 3. So similarly to what we've done in the past, we want to remember order of transformations. So we are going to apply our stretches first. So what is happening here? We have a vertical stretch by a factor of 2. Okay, so let's apply that first. So I'm going to take these points and I'm going to physically stretch them vertically by 2. So this point here is at a -2. If I stretch it by 2, that point's now going to come here. This point is going to stay the same. We can also go off this point here is at -1. That's going to be a -2. So we kind of get an idea of what this graph is going to look like. So I'm going to faintly put it in here as a dotted line. So there's my stretch. There is no horizontal stretch. There is no b value, so we don't have to worry about that. Okay, so that was step 1. Now we're going to apply our vertical reflection. So we're going to reflect this in the x-axis. So this point is now going to reflect to here. This point is now going to reflect to here. This point's going to stay the same. All of these points are going to reflect down here. So now we do a little bit longer dotted line. Okay, so this is after the reflections. And then I am now going to move this graph 1 left and 3 down. So because I'm moving this 1 left, this is now my new horizontal asymptote. So I'm going to highlight that here. So I'm approaching this line but never touching it. So my vertical asymptote occurs at x equals -1. So I'm going to move all of these points 1 left and 3 down. So this point here goes 1 left and 3 down. Here we go. This point here, 1 left and 3 down. And this point here, 1 left and 3 down. So our final graph is going to look something like this. Okay. All right, so always just remember order transformations applied in three separate steps if need be. Okay, if you can't do it all in one. Okay, moving on. describe how the function y equals log f base 5 of x is related to the graph of y equals log base 1/5 x in terms of transformations. So what I'm going to do is I'm going to kind of rewrite this logarithmic function so it's going to end up to be in a base log 5. Okay? So in order to do that, I'm first going to rewrite this equation in exponential form. So if I rewrote this in exponential form, my base of my power is going to be 1/5. My exponent is going to be y, and this is going to be equal to x. I am now going to write this as I'm going to change this to a base 5, because that's what this logarithm is in. So if I change this to a log or an exponential power of base 5, this would become 5 to the negative y equals x. So now what I'm going to do, now that I've written this in a base 5, I'm now going to convert it back to a logarithmic form. So if I change this back to logarithmic, I get log base 5 of x equals a negative y. So if I solve this for y now, by dividing both sides by negative, I get negative 5 log base 5 of x is equal to y. So if I compare this to my original logarithm base 5, now we can discuss the transformation that has occurred on this in relationship to this. So technically a base 5 to a base of 1/5 is actually a reflection in the x-axis. Okay, so a log of base 1/5 x is actually equivalent to the reciprocal base times a negative. So that's an important maybe piece to remember as you start to really work with logarithms. Recognize that these are equivalent functions. So this would be a reflection in the x-axis. Example 3. Given the function y equals log base 2 of x as the solid line, write the equation of the function for the dotted line. Okay, so as a note, when you're asked to write two graphs, this is similar to radical functions, where you would never be expected to figure out a horizontal and vertical stretch combined. It's either going to be one or the other. So just make a note that only one direction of transformations will occur. So either horizontal or vertical. Never a combination of both. Okay, so what I see here is that my y, or my vertical asymptote, has obviously changed from 0 to x equals 3. So this tells me my h value. So this tells me that there is horizontal transformations occurring here, not vertical. So what I'm going to do is I'm going to start by writing out this. So because my horizontal or my vertical asymptote has changed, I know that I'm going to have a combination of horizontal transformations. And I know that my h value has to be the same as my vertical asymptote. So my h value is going to be a 3. So I'm going to substitute that in. And now I'm going to pick a new point, or a point on my new graph, substitute it in for x and y, and then I'm going to solve for b. So this point here is at 5, 0. So my y value is 0. My x value would be 5. So I have 0 equals log base 2, and this is going to be 2b, right? So 5 minus 2 is 2, 2 times b is b. So now I'm going to change this to an exponential form in order to solve for b. So I'm going to change this to 2 to the power of 0 is equal to 2b. Well, anything to the power of 0 is always 1. If I divide both sides by 2, I get 1/2. So the equation of this logarithmic function would be y equals log base 2 of 1/2 x minus 3. Done. And then lastly, example number 4. What horizontal stretch has been applied to the function y equals log 3 of x so the graph of the transformed image passes through the point 3, 3? So similarly to this previous question, it tells me a horizontal stretch is being applied. So I'm going to rewrite this equation as y equals log base 3 of bx. B is going to be my horizontal stretch. Okay. Now I'm going to, and it tells me a point on my transformed graph, 3, 3. So I'm going to substitute that in for x and y. I'm now going to change this to exponential form and solve for b. So 3 to the power of 3 is going to equate to 3b. So 3 cubed gives me 27 equals 3b. Divide by 3 and we get a b value of 9. So just be careful, this is my b value in my equation. That's not necessarily my horizontal stretch. So if I wrote this back into my function would look like this, log 3 of 9x. So my b value is 3, so that tells me it's a horizontal stretch by a factor of the reciprocal of b. Okay, and that is transformations.